So today we'll be probably doing one of the most celebrated results in fluid mechanics. I'm very excited. This is, an excellent topic, and I presume many of you have already seen the result. But I imagine that almost most of you would not have derived it before. So now today we learn how to derive it, and then just wrap up the chapter 8, which is creeping flows. I should mention before we go into details today that there are some other topics in the book on creeping flows beyond bidirectional flows, but that is something we'll not do in the class. But in case you need it for your research or you're just interested in the topic, feel free to write to me and we can chat about that separately. All right, so let's get started. Some quick announcements. Yeah, just a final reminder for midterm feedback. So we have had 50% participations and we have got some great suggestions. So if you want to, suggest some changes, have some thoughts, please, share them. But we'll start having, we'll announce the changes we will do from next week. Homework 3 grades have been posted. So please take a look. If you have any regrade requests, just submit directly on Gradescope. And then Montana will have office hours on Friday if you have any questions about homework 4. If you haven't started homework 4 yet, I again say, please start. It's a longer homework. So don't wait until the last minute to start. So start earlier. All right, so quick recap. So we'll not do the full recap today, just some quick thoughts about what we have been discussing. So we derived the governing equations, boundary conditions, and then this is the kind of overall kinds of problem that you have seen until now. So the first problem was hydrostatics. So there was no flow, velocity is 0. Simply just find pressure and you solve for forces. Then we had unidirectional flow where we had only one component to be non-zero, which was Vx, or it can be something else as a function of y. And then in that case, pressure gradient was constant. And then again, you calculated forces using a stress vector integration in your homework problem, homework 3 problem 4. Then we did nearly unidirectional flow, which is lubrication approximation, where one component is dominant. The Vx velocity is much greater than the Vy velocity, and pressure is only a function of x. And we discussed the conditions for lubrication is one of the dimensions has to be very small, and Reynolds number times that ratio has to be very small. In lubrication 2, Montana had a full lecture on force calculation. So recall that we discussed how ball bearing will, how much force the fluid layer will apply normal force, and that when you have a higher viscosity, lower gap, you have a higher force, so you can support more weight in lubrication approximation. Then last time we started with the creeping flows where Reynolds number is much smaller than 1. And then there we have this process time scale, but convective time scale to be on the order of 1. And then he said, if these conditions are satisfied, then we'll get the Navier-Stokes equation simply becomes this, and the time dependence vanishes. The system becomes almost quasi-steady or time reversible. And these equations will apply for all kinds of flows, unidirectional, and bidirectional flows. Okay, so it doesn't necessarily mean that creeping flow has to, it is just a general formula as long as Reynolds number is small, and then you can have further approximations like unidirectionality or lubrication, or today like we learned bidirectional flows. Okay, so now again recall that in last time when we discussed the squeeze flow problem, where we were discussing how if we have two plates and we're pushing them like this, and then the flow is going outside like here. We discussed this problem, right? Even here we also did force calculations. So force calculations is an important feature that I really want to make sure you kind of remember after this course, because that's one of the most important balances you will do, because you can solve for velocity profile, but so what? We really want to calculate how much force the fluid is applying, or how much weight we can hold because of lubrication, or how much drag we will have on system. So force is really important, and that's what we will do today. Okay, so today we'll focus on bidirectional flows, and that means that the velocity components are no longer, one component does not dominate. So let's take a simple case, and we are in chapter 8. Just to again remind you, we are in chapter 8. Okay, so we have a bidirectional planar flow. Okay, so bidirectional planar flow, and I'll just say axisymmetric also, and we'll discuss this axisymmetry property right afterwards. But imagine a planar flow. Okay, so imagine we are on an XY plane. So now the third dimension, the Z dimension, does not exist right now. Okay, so we are only thinking about a 2-dimensional flow, and this is just let's just focus on that, and you will see how this is relevant. And now we have a bidirectional creeping flow is valid. So Reynolds number is much smaller than 1. So we have a creeping flow condition. And then what we will have, we'll have Vx as a function of x and y, Vy as a function of x and y. And sorry, I should also note it's also a function of, it can also be a function of time, right? And then P is a function of x and y and t, okay? So we'll have Vx, Vy and pressure, and they can all be dependent on x, y, and t. And so if we have this and we have a creeping flow, then we can just write down our equations, right? So our governing equations are now the continuity equation. Continuity equation, which is del Vx by del x plus del Vy by del y is equal to 0. And then our equations for Navier-Stokes are minus del P by del x plus mu del square Vx by del x square del square plus rho gx. So here the idea is if gravity is in the x or y direction, I'm just taking the x component, or minus del P by del y del y square plus rho gy. So any questions on these governing equations? Any confusion in symbols or anything? Okay, so continuity equations, the Navier-Stokes equation in 2 dimensions. Now the problem is we want to solve, but can we approximate anything further? So we are told that it's bidirectional. So Vx is basically on the order of Vy, or rather, let me put it this way: Vx comma Vy is approximately 1. Right? So can we do anything, right? I mean, we have 3 equations. Obviously, this is a mess. I mean, we have all these 3 equations. Can we solve them or simplify them somehow? And from scaling analysis, this is typically what we do, right? We do scaling analysis, but we can't ignore anything. Like if I knew, okay, well, y is very small, then maybe I can cross off some of the terms or something, but I don't have that information. They are both finite. So what do we do? So the idea is, well, we have 3 variables. Obviously, that's very hard to solve. So what can we do is we want to basically reduce the number of variables. So that's a simple idea is, well, we have 3 equations, 3 variables. Previously, we had some geometric formula or some constraint to further simplify the equation. But right now we are out of options, and we obviously cannot solve all of them coupled directly. So what's the idea? The idea is we'll reduce the number of variables. So one of the ideas is to create, let's create a variable. We will call it stream function. So Vy is minus del psi by del x, where psi is the stream function. And why are we even allowed to do this, right? What I'm saying is I represent some function psi. When I differentiate it with y, we get Vx. When I differentiate it with x, we get Vy. Why is this allowed? This is allowed because if I was to take del Vx by del y, so del Vx by del x, I will get del square psi by del x del y. And if I take del Vy by del y, I'll get minus del square psi by del x del y, right? And so my continuity equation is automatically satisfies. Let's call this 1, 2, and 3. So satisfies 1, right? So if I substitute this, essentially by writing it like this, my continuity equation is already valid. So that makes our life easier in the sense that I have 1 less equation to deal with, 1 less variable to deal with, right? So the idea is to decrease the number of variables. So once we do that, then we'll say now let's modify 2 and 3. So modify 2 and 3 with psi substitution. And that will be 0 is equal to del x. Now note that Vx is del psi del y, and I'm taking a derivative 2 times the derivative with x, so I'll get a del cube psi del x square del y plus del cube psi del y cube plus rho gx. Okay, that makes sense. So I have just substituted this expression here. Okay, just substituted there. So the second derivative will now become a third derivative. Now the del x del y, and then the second derivative of y will just become a third derivative with respect to y. Any questions for this first modification of its psi? All make sense? All right. Okay. So this is my, let's say 3a, just to, sorry, 2a to get the equation. Now let me do another one, and that is 0 is minus del p by del y. Now I'll have a minus sign naturally because I have a minus del psi by del x for y term, vy. So now I will substitute these two are here. And then I'll get del cube del x square del y plus del cube psi by del x cube. Maybe I should write it opposite so that don't get confused. Del x cube plus del x del y square. Okay, so this is the substitution for this one plus rho gy. And gy and gx are just gravities in x and y direction. Right, any questions till this point? Any questions here? What we did here? So all we did was we said we have this continuity equation to deal with. Let's reduce that by creating this capricious function, stream function, and then we substitute, we get two equations. What else can we do now? Can we do something else to further simplify the equation set? Can we try to do something else that we see here that can help us? So we want to reduce the number of variables, right? So that's the idea. So one idea we see, we have a pressure here, and if I differentiate the 2a by y and differentiate this by x and subtract, then I will get rid of the pressure term too, right? So I just want to reduce the number of variables because it's very complicated to solve coupled variables. So now I want to further reduce. So we'll say, well, let us do simplify del by del y of 2a minus del by del x of 2b. Okay, so that's the idea. And what you will see is the pressure term goes away because del square p by del x del y will get cancelled. And what you will get is mu del 4 psi del x square del y square plus del 4 psi by del y4. And then you will have another one del 4 psi by del x4 plus del 4 psi by del x square del y square is equal to 0, or 0 is equal to del 4 psi by del x4 plus 2 del 4 psi by del x square del y square plus del 4 psi by del y4. Okay. Does it make sense? So all we have done is we have subtracted the negative sign. When you subtract the mu term and the 2b will become plus. So all of these terms get added, and we get a fourth derivative with x. Sorry, the fourth derivative with y, not second derivative. The fourth derivative with y here. And then we have a 2 del 4 psi by del x by del y square. Okay. And this is basically known as the del 4 psi is equal to 0, or del square of del square psi is equal to 0 in vector form. So this is the beauty of the system, is that we get one variable equation now from three variables. We are able to reduce the equation set into one variable simply by going through the steps and creating a stream function which is able to satisfy this equation. So now in creeping flow, remember the stream function is this del 4 psi of 0, and pressure, because in the last lecture we discussed the pressure follows Laplace equation. So we also have this equation that del square p is 0. Don't forget that. We'll not use it as much, but still you should remember that this is the equation set. Okay, any questions at this point? Yeah.
How can you broke it up into two separate equations? What if
Oh, no, it's
like-
the same equation. I meant to say, maybe I should have clarified. So sorry.
Oh.
Yeah, I was just trying to say del 4 operator is del square of del square, basically. So you first take a Laplace and then you take another Laplace. That's the operator. Yeah, it's only one equation. Good question. Any other questions? Okay. All right, so we have this. So what's okay? So we got this equation, great, but what's the point? So the idea here is this, that we can get these equations, and let's do the full screen here. So here, if you do it here, this is table 6-10, 612. So I'll write it just to make sure, table 612. And what this table does is says that, well, we derived right now the top portion. Okay, so we just derived the top portion, and we only derived for the case for creeping flows. But you can actually derive the entire Navier-Stokes equation just with psi. So that's the advantage of stream function, is that you can reduce the variable. So, but in the left hand side, you can imagine that the right hand side is the viscous term. So you have mu by rho. So if that is dominating the left hand side and it completely goes away, and you only get del 4 size. Okay, so does it make sense that the right hand side essentially is the one creeping flows that we want? Okay, so next to the equal to, the left hand side is the inertial term, the right hand side is the viscous term. The viscous term will dominate in creeping flows. So now this tells us that stream function is great, but it doesn't mean that I can solve it I can just use it anytime I want. I have to be restricted in the kind of flows. So if you have only two components like Vx and Vy, Vr and V theta, Vz and Vr, or Vr and V theta, then you can use stream function, and you cannot just use stream function anytime you want. Okay. The second thing you should notice that the Laplace 4 can sometimes be this E square or E4. E is just another operator in a different geometry. So it's an analogous version of Laplace, but a Laplace, spherical Laplace does not hold here. Slightly modified Laplace. Okay. So you have to be careful and choose the right condition for the data. So that's the idea, that we have this set of equations, and all of them will be or del 4 psi of 0 or E 4 psi of 0, depending on the condition you follow. So let's go back. And what I mean to say, depending on flow, creeping flow equation would be the del 4 psi is equal to 0 or E 4 psi is equal to 0 in creeping flows. So this is the beauty of the system. But now the advantage of the system is that we are no longer restricted for any one velocity or one velocity dominating. We can literally solve for two-dimensional velocity profiles. Okay, so that's the idea. Any questions at this point? Any questions about this idea of stream function or the table or anything? Yeah. Great. So you will still have only so we'll discuss an example. You will still only have the velocity boundary conditions. There will just be derivatives of psi. So you don't change your boundary conditions. Your boundary conditions still remain the same, but you just basically essentially represent them as derivatives of psi instead of this velocity, because you're solving in terms of psi. So we'll discuss the example a little bit more. Any other questions? Okay, so it makes sense. So now we have in our toolkit, right? So initially we had unidirectional, near unidirectional. Now we also have bidirectional flows in creeping flow approximation, and now we'll solve this celebrated, result of Stokes drag. So this is example 8.4-2. Example 8.4-2, and this is flow past a sphere. Okay. Flow past a sphere. So we have a solid sphere. Let's not use this color, maybe a gray color. We have a solid sphere. It is sitting in the fluid medium, where the fluid is flowing around it. and the velocity here is like the fluid is coming like this, twisting itself, and then going further. The velocity of the fluid is given as UEZ, and the Z coordinate points here, the radial coordinate points here, theta and RZ, theta and phi. So this is the idea that the velocity is coming from the, coming from the bottom, going up in the Z direction, and there is no gravity right now. Think of it almost like sphere is this, and you're going in this direction. The first thing is to remember is the radial coordinate system. Sometimes I know students get confused. I just want to quickly remind everyone. So X, Y, and Z here. Then this is R, theta, and phi. Okay. So remember that when you have X, Y, and Z, so if X is this, Y is in the plane, then phi is in the XY plane. So, right, so just think of it like this, that if we have this, then this is the direction of phi, okay, and this is the direction of theta. Okay? Just make sure that that's clear in your mind. And we have been basically the flow is happening in this direction, so it's in the only the Z direction. That's what's going on. So what will happen is the fluid is coming in, going out, and then recovering from this disturbance because of the solid. Solid is stationary. So the difference now here in the, and you will see in this problem is there is no geometrical constraint, right? I have some almost like an infinite system. Initially I was at a channel or some sort of a geometry which was thin. Now I don't have the thinness, right? It's just infinite outside. So I have to solve the solution basically even far away. And so that's the difference. And this problem, and you can imagine that this makes sense, that del by del phi is 0, or it's axis symmetric. And what does it mean for, like, in the physical sense is that imagine I'm cutting a slice here. I can't choose a difference, sphere is the same in this direction. Phi direction is the same. Things are changing across this direction and the theta, which is this direction, but along the plane of each plane, it's the same. It doesn't matter where I stand here or stand at the back, that's the same thing. Phi is there is no dependence on phi. Okay. Any questions on the geometry of the problem? So the goal is to calculate velocity profile and force. So calculate velocity profile and drag force. So that's the goal. But any questions? All good? Okay. Cool. All right, so how will we approach this problem? Any thoughts? And sorry, I should mention Reynolds number is less than 1. It's a creeping flow problem, which means that rho u r by mu. Some people also use diameter, so it's just same thing. Okay. Any thoughts on how we will approach? So it's creeping flow, right? And what are the components of the velocity we can expect? We can expect we will del by del phi 0 and also v phi 0. There shouldn't be flow going across a circle. So we will expect that we have VR as a function of r and theta. We should expect v theta as a function of r and theta, and we should expect p as a function of r and theta, right? So pressures and the two velocity components can depend on r and theta. Okay, does it make sense? So what is our governing equation? So whenever you want to start now, what is the governing equation? Any thoughts? It's a bidirectional system, and Reynolds number is small. So what is our governing equation? It's the stream function. Because we can still use the Stokes equation, but we'll run in the problem that we have pre-coupled equations of pressure, velocities, and we'll not be able to solve them because it's much more complicated. So we'll go to the table. We'll say, okay, which column are we on? So which row? Sorry, so is it row number 1, 2, or 3, or 4? Which fourth, right? So we are in the spherical system, and we have only r and theta. We don't have any phi. So the thing you need to remember from this table is that we only want to say the right hand side. So this is equal to 0. And I have a definition of VR and V theta given already so that it satisfies continuity. We don't have to do that hard work. And we have been given this operator. Okay, so it's complicated. It's not really once you get once you see one example, it's very straightforward. It's like a process. You go to this table, say this is equal to 0, look up the value of VR and V theta and the operator E square. Okay, so let's do that first. Let's just copy this value of the table in the notes. So we have VR definition. So governing equation is E4 psi is 0. E4 psi is equal to 0. Then where we have VR and 1 by R square sine theta del psi by del theta, and V theta is minus 1 by R sine theta del psi by del R. Next we have E square, which is the operator given to us in the table, del square by del R square plus sine theta by R square del by del R and sine theta del by del theta. So this is basically the operator. I've literally taken down it from the table. This is not something that you will be expected to do, or literally just geometrical transformations of the coordinates to get to this sort of stream function. Okay, so you get this. We have the governing equation now. So we have the governing equation in terms of psi, and the velocities. So what is really left is we need to figure out the boundary conditions. Okay, so the second step is boundary conditions. So boundary conditions. So what do you think are the boundary conditions here? Let's go there. What are the boundary conditions? Yeah. Great. So we know the velocity far away. That's one boundary condition. Any other boundary condition you know? What else? No slip and no penetration, because nothing will go into the surface. It's not a porous material, right? So no slip and no penetration condition. So we'll say and the velocity far away. So let's first do the no slip and no penetration, that VR at r comma theta is equal to 0 and V theta at r comma theta is equal to 0. I hope this is clear to everyone, that V theta is the parallel component and then VR is the perpendicular component, right? So both of them will be 0 because no slip, no penetration, and no slip. Okay. All right. So any questions on this? Any questions on this? So how can I write in terms of, so this is in VR and V theta, but I am not solving in velocity, I'm solving stream function. So that means that this is equal to 0 and the VR and V theta is equal to 0, right? So this means that del psi by del theta is equal to 0, and that means del psi by del R is equal to 0. Does everybody follow that? I can substitute VR is this formula, right? From the stream function. If I substitute that, that means that del psi by del theta is equal to 0. And if I substitute that formula, then I'll get del psi by del R is equal to 0. Okay, makes sense? So what I'm saying is, you will substitute this here and here to conclude that del psi by del theta at r equal to r is 0 or del psi by del R. Okay, does that make sense? Anybody have a question on this? All right, so we get this boundary conditions, two boundary conditions now, and the last boundary condition is what Ritu said, that we know the velocity far away. That's been given to us. That's UEZ. So velocity far away. Any questions? So velocity far away is UEZ, right? That's been given to us. So we have been given that velocity far away, u easy, that's the velocity that is through which I'm flowing the coming over the sphere. So how will I get VR and d theta from this? Anybody has thoughts? I have been only given a z component. So how do I go from there to r and theta? Shift the coordinates from Cartesian to correct. So that's one idea is exactly that. So you shift the coordinates, but you can basically look into the table here, right? So let's look at the table. You have ER, E theta, EX by EC. So you really want to go to this, right? You find 1043. You want to substitute this ER as EZ as in terms of ER and theta, right? And then you have two components in the R and theta. So the last 8.746. So substitute that and then solve this solve this problem here. Okay, so what are the boundary conditions far away? So look at this first and then try to substitute and get VR and d theta. Okay, so let's see. So did everybody get? So what is the correct answer? It should be. Anybody wants to volunteer? It should C, right? Because if we go here, we had U easy. We'll substitute ER as E cos theta, sorry, easy as minus sin theta, E theta, which is what you will do here. And so you can compare and get to this complete. Okay, any questions on this? Boundary conditions till now. It's important to see how we are switching from Z to R and T. I want to make sure it's clear. Questions? Good. Okay. So now we have this free stream boundary condition, which is far away. And like we did, we'll substitute the value of VR. So this is equal to VR, right? So this is essentially equal to minus 1 by r square sine theta as r goes to infinity, right? And the other one is let's do this. As r goes to infinity. Okay, so what I'm doing is I'm saying now because we need the boundary conditions in terms of psi, I will say when del theta as r goes to infinity is really u r square sine theta cos theta, and del psi by del r is minus u r sine square theta. Sorry, plus u r square sine square u r sine square. Okay. Is there a mistake? I think I may have made a mistake with a minus sign. There is no minus sign here. Sorry about that. There is no minus sign here. So this is u r square sine square theta. Yes, both should be plus. Okay, and this is also r goes to infinity. This is the boundary set condition. Okay, yeah, go ahead. Infinity. Yeah, it is r goes to infinity. Yeah, so stream function of rate is going to infinity. And we'll see how, because it's not velocity, it's still stream function. The stream function doesn't have to be bounded necessarily. So we'll learn, but yeah, you're absolutely right. It looks a little bit strange that your R is going to infinity and the type of infinity is going away, but because we have stream function and velocity, we are allowed to do that. Because our velocity is still u, and it is given as u and u cos theta and u sin theta. It's just the transformation is going. So our velocity is still finite. Any other questions? So now is the part which is slightly could be a bit confusing and doesn't always not even always easy to see, is that both of these, they are one is derivative with respect to theta and one is derivative with respect to r, and you can see that if I write psi as r equal to infinity, I can write u r square sine square theta by 2. And I understand this may not be always obvious. Sometimes it's not always clear how you came up with that, but this is where you basically have to carefully look at that. And you can see that the derivative of sine square theta will be sine theta cos theta almost, and 2 times also, and then r square derivative will be r. So that's why you basically say as far away, I can simply say stream function u r square sine square theta, and that will automatically satisfy these two boundary. Combining in a way my boundary conditions. Okay, does that make sense? Any questions? So differentiate this. If you differentiate this, you will get this. If you differentiate this with respect to I, you will get this. So basically, both of these boundary conditions can be combined into this one condition. Okay, that's the idea. And why are we doing this? I mean, why not just leave it them as u r square sine theta and in terms of derivative? The problem here is the whole issue in this problem is it's a bidirectional system. Have an r dependence and have theta dependence, right? So that's the problem. We have an r dependence and theta dependence, and when we see that, this gives us a clue that maybe the sine square theta dependence is sort of going to stay throughout. So what, and this is the genius of the Stokes result, is that it was then proposed that looking at this, getting inspired from this, taking inspiration from this, then taking clue from this limit, Stokes proposed psi of r comma theta, which is what we want to solve. Psi of r comma theta is in the form of function of r comma sine square theta. So this is the genius of the Stokes result, is that, well, we get to see that at infinity there is some sine square theta going around, and I definitely know things are changing with r. I know the velocity is 0, and the surface I know the velocity is u easy far away, but this theta dependence is really bothering me. So why don't I just say that the sine square theta dependence will be carried throughout? And this is a guess. This is not an exact formula. And if this guess is correct, we will be able to fit this into our governing. So like you saw in one of the initial similarity transform, we guess a solution and then we see whether it satisfies the governing equations and boundary conditions. So this was the guess by Stokes. And when you do that, you substitute, and this was this, you substitute back and you are able to get it. And it does satisfy. So the idea is not random. Sometimes, students saying, well, this doesn't make any sense. It's basically literally taking a clue there, and well, can I just use that sine square theta and say this f of r is a function of r, which I will solve. So this way, we started with dr v theta pressure, we reduced to psi of r and theta, then we wrote boundary conditions, and now literally we have even removed the dependence in theta. We have just gone to the dependence of r. So we have gone from dr v theta p to psi and then to f. It's a function of r. So it becomes an ordinary differential equation and doesn't even mean a partial differential equation. Okay. So let's take a 5-minute break here, and then we'll continue to look at the velocity profile after that. So take a 5-minute break. So right now it's 12:44. So let's start at 12:49, and then we'll start discussing that. Yeah, good. Yeah. Yeah, that's a great question. So it is difficult, and you can see that, I mean, we didn't discuss this in class, but sometimes undergrad textbooks talk about that quite a bit, is, how if you integrate stream function, you get a flow rate. You might have heard of this. So if I'm going, yeah, here. So if you're going, let's say there are two stream lines, the psi is the function, right? So contour, like, create a contour of constant psi, right? Then if I just integrate, I get Vx dy, right? So Vx dy, so I'm going from one side to another side, I'm kind of getting a flow. So physically, it's really like the path that if I use a particle that's a function, without a stream line and such, one of them are another, but it essentially represents the shape. Because with the T streamline, the flow rate, but I certainly am not like very familiar with this technique. I did talk with streamline and path line and streamline. So for I have really ordered mathematical function, but there are different reasons. One is flow rate, and the other is that if you differentiate it, you get which is always on the map. Any other questions? Before we go further? This was done in 1850. And at that point, without any computers, any calculations, no calculators or anything. At that point, somebody figured out how to reduce a three variable problem into an ordinary differential equation. And it's really inspiring to think about how all of this process was done, back 160 years back, almost 1852, I believe. All right, so let's begin. So 1249. So till now we have discussed that the governing equation is a stream function. Then the no-slip boundary condition becomes the del psi by del theta, so del psi by del r, and the del psi by del theta is a penetration condition. And then far away we get this result from the stream functions. Okay. Now the idea is Stokes proposed the left-hand side. So we know the value of E square. So E square is given as and we will not do this in class. I will just give you the step. So E square is really del square by del r square plus sine theta by r square del by del theta sine theta del by del theta. Okay. So you can substitute the psi as this. You can substitute the psi here, right? And sorry, psi as f of r. So, and your governing equation will get modified. So your governing equation will get modified, and this is a step I'm skipping. In your homework problem, you have to do this. I don't remember if you have to do this, but you will be using a very similar approach, but there it's a bubble instead of a particle. So your boundary conditions are naturally going to be different. So this is the operator that you get in your, if you modify it. So the first thing you notice is that it actually does work. The substitution does work. So substitution holds. Substitution works. Okay. For the governing equation. Okay, so substitution works. Then the second thing is the boundary conditions. Now the boundary conditions will become del psi by del r. If you clearly see, it's simply df by dr. And r is equal to capital 0. Then if you differentiate with theta, you get something in theta. So you get f of r equal to r is equal to 0. So that's this one, second boundary condition. Then finally, when r going to infinity, you get ur square by 2. So this is now my new set of governing equations and boundary conditions that can give us the stream function and the stream function. Okay, and I skipped the step of deriving the governing equation, but I hope you will be able to do that at home. It's very instructive. I remember I got an email from a student in Netherlands who said, "Oh, I'm not able to get this." So the student actually tried to derive it. And so it's very instructive to derive it and see it is helpful. I think that is a lot of lot of learning here is really doing it and making sure you're able to follow all the steps. So unfortunately we can't see that step in class, but it's good to try that and any questions about governing equation boundary conditions? Yes. Oh, that's the second operator. Great question. So maybe that's an excellent question. So the first is the e square, and then we have another e square. So you basically have, because it's a code, so you first find that and then you do the operation again on that. And we'll see how we do it. So it's not, there is no f because this is an operator essentially. So this is operating on this. So this is operating on the function g, which we will find, which is in the brackets. Okay. So we will solve this. We'll solve this in a second. It will become clear. Any other questions here? So you see the process. Two velocities, pressure reduced to stream function reduced to f of r. Now we have a differential equation that we can solve. Ordinary differential equation. Okay. So that's the idea. So now let's see how we can solve this. And so this is something you have not seen before. This is something you don't have to worry about. Just remember in spherical coordinates. In spherical coordinates, solutions often look like, solutions can look like polynomials. So r raised power of n, where we do not know the value of n. Okay? So they can look like this, r raised power of n, where we don't know the value of n. This is very common in spherical coordinates, and you don't have to worry about it. This is just a property of spherical coordinates. So we can try to substitute this. So substitute f of r as r raised power of n. Okay. So if you do that, d square f by dr square would be what? So df by dr would be n into r to the n minus 1. So I'm just doing a polynomial differentiation. D square f by dr square would be n into n minus 1 r to the n minus 2, right? So that's what we will do. And then 2f by r square is 2 times r to the n minus 2. Okay. So d square f by dr square minus 2f by r square is equal to n into n minus 1 r to the n minus 2 minus 2 r to the n minus 2 okay, and this becomes n squares. This is n square in case it's confusing. N minus 2 into n plus 1. This is the value of d square f by dr square. Okay, so we have substituted this polynomial function, and again, like I said, you don't have to worry about where this came from. This is a classical way you substitute in spherical coordinates. So you get this for first portion of the governing equation. So this is the idea, right? We're trying to solve the governing equation, and we're guessing that the function would have some r to the power of n that will satisfy the solution. Now we did this exercise and we got this. And can someone think through a shortcut of how I can simplify the? So now I have to take another same operator. So if you look at one on top, d square by dr square minus 2 by r square now has to be done on this formula, right? So can you see any trick? Do you see a trick with so that I don't have to do the same exercise again? Can you think of a trick? So let me put it like this. So you can imagine that now I have to do this. I have to say d square by dr square of minus 2 by r square. So put in governing equation. So this is what I'm doing. Put in governing equation. of an equation, and this is r to the power of n minus 2, n minus 2, n plus 1, right? So this is what I have to do. And this really is equal to n minus 2 into n plus 1 d square by dr square minus 2 by r square of r to the power of n minus 2, right? This is all, I mean, I'm just substituting this. So the trick here is that now I'm doing the same operation of r to the power of n minus 2. On top, I just did r to the power of n. So essentially, I can substitute in the result that you see on the underlined line. I can substitute n as n minus 2 and write out the result. Right? I don't have to do the whole calculation again. I can simply say substitute here. So this will become n minus 2 into n plus 1 into r to the power of n minus 2 minus 2, n minus 2 minus 2, n minus 2 plus 1, or this will become n minus 4 into n minus 2, 1 plus n plus 1 is equal to 0. Okay. So what I have written here, I've substituted in this solution. If you think of this portion of the solution, this is exactly the same as this one, but where n has been substituted as n minus 2. That's all I've done, because I'm applying the same operator on a smaller. Okay. So all of this hard work finally gives us the solution that I can expect n to be 4, 2, 1 minus 1, to 4, 2, 1 minus 1, and finally, that means f of r is a r to the 4 dr square plus cr plus d by r, where a, b, c, d have to be found through boundary conditions. Okay. All right. So any questions here? I know this is a lot to digest because it's a pretty mathematical heavy exercise, but I want to make sure that we are able to go through this. And you just have to do it once. You will really remember the process once you do it. In homework, you will do this yourself. Okay? Any questions at this point? Okay. So you can find A, B, and C, A, B, C, and D from boundary conditions. I will just give you the results. A is 0. It's not very difficult to see actually. A is equal to 0. B is equal to u by 2. C is equal to minus 3u r by 4. And D is equal to u r cubed by 4. Okay. So from boundary conditions, if you apply, and the boundary conditions are here. Okay. So these boundary conditions. Just apply there and you can find the value of A, B, C, and D. And this is what the result is. So finally, all of this hard work then gives us psi of r theta. Psi of r theta is u r squared sine squared theta. R by r whole square by 2 minus 3 by 4 r by r. So capital R by small r plus 1 by 4 r by r. Okay, so we finally have found the stream function solution, which is the idea behind bidirectional flows. Is first you start with the stream function solution, use the boundary condition to propose a separation of variables kind of method. We found f. So now we also have a solution which is for stream function complete. So now a function of psi of r and theta. Okay. So how will I find velocities? So now that I have stream function, how will I find velocities? Right, because we have already written the formula, right? So we know the formula for velocities. Once you know psi, you can just, sorry, not here. This is the boundary condition. The formula is here. So we just substitute it here and we have the velocities. Okay. So you get the velocities. I'll also give you the velocities here. And in a homework problem, you will do a different problem, very similar but different, where you will actually find the velocities. So you will get that practice. So VR is u cos theta 1 minus 3 by 2 r by r plus 1 by 2 r by r cube. And then V theta is minus u sine theta 1 minus 3 by 4 r by r minus 1 by 4 r by r cube. Okay, so this is finally we have velocities by using stream function definition. Okay. All right. So all of this hard work finally gives us this, and this is an amazing result. I mean, this is amazingly beautiful. Let's put small r as capital R. You don't have to think about all the math. You see, we put small r as capital R, you get u VR is equal to 0, right? 1 minus 2 by 2 plus 1 by 2, 0. So velocity VR is 0. If you put small r as capital R in the denominator, again, d theta is 0, so no slip and no condition are satisfied. If you put r equal to infinity, then you will have all of these exponents drop out and you get u cos theta and minus u sine theta. These are our boundary conditions for VR and d theta. That means the net flow is in the positive increasing direction. That is what we get in force. Okay? And Sam, to your point, as you can see, the solution does not blow up. Even if the stream function was going to infinity, because of my relationship with velocity, this is a completely bounded solution that I get. Okay? So for those of you who are more inclined towards trying numerics, I really encourage you to try this to make a vector plot in MATLAB. It won't take too much of your time. You can make a vector plot and you can see literally visualize all these streamlines or velocities going through the sphere. You can see how symmetric they are, how they look. It's pretty easy to do this in MATLAB. And I'm happy to chat about that later if somebody's interested. Okay, so we have this. So let's go back. So we started the problem here. So we said the problem here is axis symmetric. We have the theta. We want to calculate velocity profile, which we have done, and then we have to calculate drag force. So how do we calculate drag force? Any suggestions? How will we calculate drag force? Thoughts? How do you calculate force? Which formula do you use? S and ds, which is the stress vector times the surface area. That's always, whenever you calculate force, you have to go there. Okay. All right. So we will do that. Before that, however, one thing is missing is that we don't have pressure. Okay? So one thing you might have seen is that we eliminated pressure in this approach stream function. And so that's the thing. Although we can solve the velocity, we still don't know pressure. And to solve for pressure, what you do is, and this is something you are not expected to do, it's a very long derivation. So you substitute Navier-Stokes equation in NSC to get P as, and I'll just give you the result. You don't have to derive this, but I'll just give you the result. Minus mu u by r by r square cos theta. Okay, so we have this, we have this, we have this. So the three variables we needed for our equation. So this is substitute in NSC and then you integrate back to get to this solution. One thing you should note is that VR and V theta are at both the same scale. Okay, so it's a truly bidirectional problem, that there is no difference in scale. They're both on the scale of U. And pressure, as you can see, is scaled by mu u by r. Mu u by r, which makes sense. This is the viscous stress, because pressure and viscous stress are being balanced by balancing. Okay? So that you can see some beautiful scaling also coming through this result. All right, so now if you want to calculate drag force, so to calculate drag force, we say we have F is S and ds. Okay, this is our Z R. We want to calculate drag force by the fluid on this sphere. So please volunteer and suggest what is the normal component here. If I want to calculate drag, what is N? ER or minus ER? Should it be this or this? Positive ER, right? Because it always points into the fluid. Okay, so it always points into the fluid. So it is ER. Okay. How will I find DS? Thoughts? How will I find DS? We've done this now several times. Is that you look for the coordinate that is constant. Right? So what is constant in on the surface of the sphere? R. It's capital R. So you will go here and you'll say, well, I have the DSR mathematics. We choose this because R is constant. So it's R squared sine theta d to the d phi. Where R, small r is capital R because it is constant. So it's R squared d theta d sine squared theta. This is R squared sine theta d phi. And that's where theta goes from 0 to pi and phi goes from 0 to 2 pi. Okay. Recall you did something very similar when you were doing the buoyancy problem in the homework, right? So this kind of hopefully gives you an idea. Now finally we have a stress vector. Stress vector is minus p del plus tau, and it's only two-dimensional. Okay, so this is your minus p delta plus tau. So you have tau r, r theta, and tau theta theta. And when you substitute that back, you can calculate the drag force. We are not going to do this in class. I have already prepared a supplementary video, which is what I'm going to upload. Please try this. This is very instructive. This is one of the most important results in fluid mechanics. So it's very instructive when you do it yourself. So what is the challenge here? The challenge here is we are in ER and in theta. But remember, whenever we are integrating a vector, we cannot integrate if the direction is changing. ER and theta are in collinear coordinates. So you take ER and theta components, you substitute in terms of EX, EY, and EZ, and then you integrate. And finally, what you will get out from this is the result that all of you have seen before, that drag force is 6 pi mu UR EZ. This is the drag force that you get out. Okay, so we will have a supplementary video for this, so you don't have to worry about the derivation, and it will walk you through the steps. Okay. But this is the drag force. This is the Stokes drag force, and this is very highly used result even today. A lot of diffusivity. You might be doing diffusivity measurements in your lab. That's based on Stokes drag. You might be doing some sort of microfluidics lab where particles are moving, droplets are moving. Stokes drag comes there too. The Stokes drag is really a very crucial result and has really shaped fluid mechanics. Okay, so how much time do we have? Okay, we have 10 minutes. So any questions on Stokes drag? How we came about this process? Yeah, for example.
So the pressure you look at the equation, is that based on what's the reference pressure?
Absolutely beautiful question. The reference pressure is as far away as possible. Absolutely great question. If it is atmospheric, you will have a P naught plus something. But as you can see, if you do add a P naught, then if you integrate it on the surface, it will just go away. So reference pressure will not matter for the force drag, right? Because if it's just P naught and I'm integrating it throughout the surface, on all directions it will just cancel out. So P naught is not important. That's why the reference pressure has been chosen to be 0. Great question. It can be something else. I will be about to go to that question just in a second. But great question. Any other questions? So any thoughts on how we will calculate this tau RR and tau R theta? Anybody remembers? How will we calculate this? We don't know these numbers. How will we calculate these values? Thoughts? Yeah, go ahead. Absolutely, because we are in V theta, you simply have this table, right? So which gives us the expression for tau RR, tau R theta. So you just use that table to find the derivatives, and you have the shear stress. Okay, so that's something you'll have to do if you do it. And in the supplementary video, I walk through those details, some of these details. All right, so we get this. So first, few things to note. First, drag force in the direction of E of velocity. Drag force is in the direction of fluid velocity. Relative fluid velocity. Okay. You should note that. And does it make sense? Does it make physical sense? It makes, right? That if the fluid is flowing over a solid sphere, it is trying to push it in its own direction, right? So that physically it has a lot of meaning. So what we will do in your homework, so I just want to clarify this in your homework problem 4, you will be calculating this on a bubble. You will have air and then you will have fluid around it. So can anyone tell me what will be the difference here? The whole process and the whole process. Same problem, exactly same. So what will change in the entire process? There is only one thing that will change. When the boundary condition at the interface, at the air liquid interface, we don't have no slip. We have no shear stress, right? That's the condition that we remember. So that one small change will change everything in the derivation. So you can see the importance of these boundary conditions and governing equations is that one small change changes the entire process. So that's what you will do in your homework. But I just wanted to kind of give you an idea that you'll calculate that. Okay. All right. So we are done with Stokes drag. I just quickly want to discuss a small topic of terminal velocity. Terminal velocity. And this is a well-known solution, and some of you, I believe, must have seen this also, is that if I have, let's say some sort of fluid here, and I have a solid flowing through it, solid dropping through it in gravity. So if I have a solid, and let's say this is dropping here due to gravity, it has some u terminal velocity, okay? U terminal velocity, and gravity is in this direction, equal to minus GeZ. Okay. The density of the fluid is rho s, and the density of the fluid is rho. So if it is falling through this viscous medium of fluid, it attains a terminal velocity, right? So how many of you have seen this terminal velocity before? Velocity, yeah, right. So how do we calculate that? The idea is, so now we have done the fluid problem. So it's important to recognize this, and I went through this last time also. That once you have done the fluid problem, now we are focusing the attention on the rigid body. On the rigid body, you just use simple Newton's law. You don't have to use Navier-Stokes or anything, right? So now if I have this, then I will be applying a gravity force, right? And gravity force on a solid would be rho s 4 by 3 pi r cube Ez. Sorry, minus GeZ. So it's in the direction of gravity. Gravity is pulling it down, right? Which direction will be the drag force by the fluid? Which direction will be the drag force of the fluid falling down? Going up. Why? Because we had the solid to be stationary in the last problem. Here the solid is moving. So relatively, fluid is going up, right? So it will be on the other side, it will be, so drag force would be 6 pi mu ut r z. 6 pi mu r, 6 pi mu u r. So 6 pi mu ut r z. Is there any other force that we have to take care of on the particle? The buoyancy force, right? So you also have the buoyancy force. It acts opposite to gravity. So you'll get, and that will be the weight of the fluid displaced. So now we'll have rho, what we use for the density of the fluid, because it's the weight of the fluid displaced. And you do this, and if you do Fg plus Fd plus Fb is equal to 0, this gives you the result that ut is And it's a very small derivation. I'm sure you can all do this. R square G by mu minus EZ. So it does drop. Sorry, actually, my mistake. I think I already have it as a magnitude. So this is what you will get. Okay? You will get 2 by 9 rho s minus rho R square G mu. And this is what it is. Check. I hope I have not made a mistake. Yes, this is what you'll get. Okay, so you can substitute this. So the idea being that, okay, now we have the drag force, so drag force will help us calculate terminal velocity. You can see that the terminal velocity is going down if rho is greater than rho. If I have a light solid, which is small, lighter than water, the velocity will be negative, which means it will go up. It will go up, right? And in that case, your drag force, if ut is negative, my drag force will reverse its direction because the fluid will then push it down, right? So it kind of goes, depends on the direction of the velocity of the solid. One question before we close the lecture is this, that since buoyancy force is in the hydrostatic pressure force, which is what we calculate, right? That buoyancy force is basically the hydrostatic pressure force, and a drag force already has a pressure, right? So when I calculate drag, I already have the pressure force here. So aren't I double counting the buoyancy force? So when I'm doing a calculation, I have a drag force, it already has a pressure force. And then I'm saying, oh, I'll also add a buoyancy force. So aren't we double counting it? Thoughts? So what is missing here? Like,
But if when we calculated that RSC considering pressure with respect to the reference.
great. So that was the question that Sam was asking, and Alka was said, is that because the pressure profile I have calculated here, pressure profile I gave you in the solution here, does not include gravity. So the hydrostatic pressure force because of gravity, because we just said it's zero, we were not including the effect of gravity in the pressure force, and that's why we are allowed to actually basically add a buoyancy force. However, if I was to solve my governing equations assuming a gravity force, then I cannot do like two calculations. Then my drag force will itself include an effect of the buoyancy. Okay, so it depends if I have included gravity in the pressure calculation or not. It's just convenient to not include it and add it separately. That's what the reason. But you should be aware that it is possible that you can include gravity in the pressure and that will automatically. So all right, so that's it for today. In the next week, we'll start implicit flows, which is the opposite of Reynolds number, small Reynolds number. That's infinite Reynolds number, where viscosity doesn't matter. Okay, so that's what we'll start next week, and I look forward to seeing you then. And please fill out the mid-semester feedback form if you haven't.